I'm going to talk about plane waves and their relationships with differential operators and some useful things that we can derive from these forms. So we'll start with the definition of a plane wave. A is equal to A0 e to the I k dot r minus omega t. And remember, of course, that this part, e to the I k dot r minus omega t, is the phase. Now, A0 is, of course, a vector, which we could write if we wanted to as A0x, A0y, A0z, and if we chose, similarly, we could write A as AX, AY, AZ, and the relationship between those two is that the second one is simply the first one multiplied by the phase. Now let's just think briefly about the differential of that phase part. So d by dx of k dot r minus omega t is d by dx of, and now let's just multiply out that dot product, kxx plus kyy plus kzz minus omega t, which is just equal to kx. In the same way, we could write that d by dt of k dot r minus omega t is equal to minus omega. And this then means that we can take differentials of ax and ay, so d by dx of ax is equal to ikx ax, that we just get by considering the form of the phase and by differentiating. Note that d by dx of ay is equal to ikx ay. That's an important distinction to note. When we differentiate, we bring down a factor of the phase related to the coordinate with respect to which we're differentiating, not anything to do with the component of the vector. So now we've got these different forms, let's just think about how we would act on the whole vector. So d by dt of A is equal to minus I omega A. That comes straightforwardly from those differentials we've just derived. Similarly, we could say that the divergence of A, which is going to be d by dx of ax plus d by dy of ay plus d by dz of az is equal to ikx ax plus iky ay plus ikz az, and that of course is just equal to ik dot a. Finally, we could look at the curl of A. I'm not going to write out all of the components, I'm simply going to think about the x coordinate, and that's given by day by dz minus daz by dy, which is ikz ay minus iky az, which is just the x component of ik cross A. So generally we say that the curl of A is equal to ik cross A. Finally, we can think about the second order operator, the nabla squared, the del squared of A, and that's equal to d2 by dx squared plus d2 by dy squared plus d2 by dz squared acting on A, and that's going to be given by minus kx squared, because we've got two factors of ik acting on A, minus ky squared A minus kz squared A, which is equal to minus k squared A. Now, why might we want to think about this? Well, Maxwell equations are written in terms of differential operators. So, if we take Faraday's law, curl of E is equal to minus dB by dt. For plane waves, we can transform this into I k cross E is equal to omega b. And we can then cancel the i's on both sides, and we see that we have k cross E is equal to omega b, which tells us about the relationship between the directions of the vectors. You can, of course, also take the Ampere-Maxwell law, which would in this case be curl of B is equal to epsilon naught mu naught dE by dt. That then transforms into k cross B is equal to minus epsilon naught mu naught omega E. I've removed the i's as we've gone along. Notice that the reason we have a minus sign is different between those two cases is because of the minus sign in the original Maxwell equation. Are these consistent with each other? Well, we certainly hope they will be. Let's just see how we can manipulate these. First of all, remember that epsilon naught mu naught is equal to 1 over c squared, the speed of light, and for a plane wave, a plane electromagnetic wave as in light, that is equal to k squared over omega squared. So we now have that k cross B is equal to minus k squared over omega E. We're now going to take the cross product with k on the left because we want to be able to return back to excuse me a second, we want to return back to this equation up here, k cross E equals omega b, and so we need to make sure that k cross E is there. So if we take k cross B is equal to minus k squared over omega k cross E. So we have the k cross E term that we want, and we now just have to expand out on the left-hand side. We're going to do this using the expansion formula that you can find in many different places for A crossed with B cross C, and please note that the order of the brackets is incredibly important. This will change if you change the order. That's equal to A dot C along B minus A dot B multiplied by C. Let's use that to expand out our k cross B. So that's going to be k dotted with B multiplied by k minus k dotted with k multiplied by B. What's going on here? Well, k dot B is equivalent to div B, which is equal to 0. So we can then write that minus k squared B is equal to minus k squared over omega k cross E, which of course takes us back to k cross E is equal to omega B, which we had from Faraday's law. It's a simple illustration, but it does show exactly how we can use these nice results, and you'll find that all the way through electromagnetic theory this kind of substitution is very helpful.